Today's video is about solubility equilibria. So this is a practical example of equilibrium chemistry that's applied to substances that don't completely dissolve in water or some other solvent. Lots of solids have a limited solubility in water. What that really means is that they reach dynamic equilibrium before most of the solid has dissolved. Here's an example. For AgI, solid AgI, even though we say that silver compounds with halogen anions are insoluble, that's really a bit of an overstatement. They do dissolve, they just don't dissolve very well. So they very quickly reach dynamic equilibrium, as shown by this equation. What would be the expression for Kc here? Well, Kc would include products concentrations raised to their powers, so that'd be Ag plus times I minus, both raised to the 1 power, divided by reactants. But our only reactants is a solid, and solids don't appear in equilibrium expressions, so that'd be what we'd write. This is a special version of Kc that's called the solubility product constant, or KSP for short. It functions just the same way as a regular K value does. It just has a special kind of designation. Let's find a value of KSP. CuBr, copper 1 bromide, has a measured solubility of 2 times 10 to the minus 4th moles per liter at 25 degrees C. The question is, what's the value of KSP? We can set this up in a Rice chart, first of all. Here's the reaction. CuBr solid is going to reach dynamic equilibrium with copper 1 ions and bromine ions, bromide ions, in solution. Initial, this is a solid, so it doesn't matter, but before it starts to dissolve, we don't have any of the 2 ions. What's the change? We're going to lose some number of moles per liter of copper bromide from the solid into the solution, and then we're going to gain an equivalent number of both copper ions and bromide ions. So at equilibrium, we still don't care about that because it's not in the expression. This will be X and this will be X. So KSP, in terms of our chart, is X times X. But it says that X is how much dissolves per liter, which is our solubility. So that's 2 times 10 to the negative 4th moles per liter, and then we're squaring that, which gives us 4 times 10 to the negative 8th, and that's the value of KSP for this solid. Another example, bismuth 3 sulfide has a measured solubility that's given here at 25 degrees C, and we're supposed to find the value of KSP. Well, let's set up our Rice chart again. Here's our reaction. Bi2S3 solid is going to become 2Bi3 plus 3S2 minus. And then initially, we don't care about the solids. These are both zeros before there's any dissolution going on. We're going to lose some number of moles per liter from the solid phase. We'll gain twice as many moles per liter for bismuth ion and 3 times as many sulfide ions. And that's just from the stoichiometry. So that at equilibrium, don't care about the solid, this will be 2x and this will be 3x. So KSP, well, that's going to be equal to concentration of Bi3 plus squared times concentration of S2 minus cubed. But in terms of our chart, that means KSP is going to be equal to 2x squared times 3x cubed. And that's going to end up being 36x to the 5th. So what's our KSP? It's 36 times 1 times 10 to the negative 15th raised to the 5th power, which ends up being 3.6 times 10 to the negative 74th. It's a very small number, which means this stuff does not dissolve very well in water before it reaches dynamic equilibrium. This is a kind of a reverse question. Here we're given the KSP value. The question is, how much dissolves? What is its solubility at 25 degrees C? So let's set up a Rice chart again. CuIO3 2, that's our solid, is in equilibrium with Cu2 plus and 2 iodate ions. Initial, don't care about the solid, none of this, none of this. Change, it's going to be a minus x plus 2x change line. At equilibrium, copper ion concentration will be x and iodate will be 2x. So KSP is going to be copper ion concentration raised to the 1 power times iodate ion concentration squared. And in terms of our chart, that is x times 2x, the quantity squared, which is 4x cubed. So KSP being 1.4 times 10 to the negative 7th, that's going to be equal to 4x cubed. Pretty easy to solve this. Divide both sides by 4, take the cube root, and that will give you your value of x. X is 0.0033, and that's the moles per liter that will dissolve at that temperature. Let's do another one, and this will be the setup for learning about a concept called the common ion effect. Here we have a KSP value at 25 degrees C, and we want to know the solubility in water at 25 degrees C. So set up our Rice chart, CaF2 solid in equilibrium with Ca2 plus aqueous and 2F minus aqueous. Initial concentration will be 0 for the products. The change line, we're going to lose x moles per liter of the solid, gain the same number of moles per liter of calcium ion and twice that for fluoride ion because of the stoichiometry. At equilibrium then, calcium ion concentration will be x, fluoride will be 2x, KSP will be equal to concentration of calcium ions times concentration of fluoride ions squared, which is going to be x times 2x quantity squared, which is 4x cubed, just like in the previous problem. So putting our value of KSP in here, 4 times 10 to the negative 11th, that's equal to 4x cubed. And we solve for x the same way, divide by 4, take the cube root, and x, which is the solubility, ends up being 2.2 times 10 to the negative 4th moles per liter. Now, what if we wanted to know what is its solubility in a 0.025 molar NaF solution at 25 degrees C? How this is going to be different is the initial concentration of fluoride ion in our initial line on the Rice chart is not going to be 0 because we already have some fluoride ion from the NaF. Let's go to a different workspace where there's more room and solve this problem. So in this NaF solution, because sodium salts are highly soluble, there's no reversible arrow here. This is going to completely split up to give you Na plus ions and F minus ions in aqueous solution. And because of the 1-to-1-to-1 stoichiometry, if we have 0.025 molar NaF, we are also going to have 0.025 molar F minus after this all dissolves. So now let's do our Rice chart for CaF2 solid in equilibrium with Ca2 plus 2F minus. In our initial line, calcium ion concentration is 0, but fluoride ion concentration isn't. We start out, before it even starts to dissolve, with 0.025 moles per liter. Change line, minus x plus 2x. Equilibrium, calcium ion concentration will be x, fluoride ion concentration will be 2x. So KSP, which is 4.0 times 10 to the negative 11th at our temperature here, is going to be equal to concentration of calcium ion at equilibrium, which is x, times concentration of fluoride ion squared, which is 0.025 plus 2x, and that's going to be squared. Now, one thing that we notice about K is it's very small. The KSP value is 10 to the minus 11th, which means 2x is going to be extremely small compared with 0.025. So we can make use of a simplification here and go 4 times 10 to the negative 11th is approximately equal to 0.025 squared times x. And that makes this easy to solve. So x is 6.4 times 10 to the negative 8th moles per liter. If we recall, when it was dissolving only in pure water, our solubility was 2.2 times 10 to the negative fourth molar. That was when it was in just H2O. So the difference is pretty huge here, 4 orders of magnitude. That's 10,000 times less soluble with that fluoride ion already present. That's called the common ion effect. The common ion effect is that solubility decreases in a solution that contains an ion common to the solute. Like we saw in the last example, fluoride ion was in our solution already, but that's common to calcium fluoride, and so that reduced the ability of calcium fluoride to dissolve. An application of KSP is predicting if a precipitation is going to occur when you mix two solutions together. Here's an example. If we had 750 milliliters of a 4 times 10 to the minus third molar CeNO33 solution, and we added it to 300 milliliters of a 2 times 10 to the minus 2 molar potassium iodate solution, will CeIO33 precipitate. So if that was happening, this is the equilibrium that would be at play here. CeIO33 solid in equilibrium with Ce3 plus and 3 iodate ions. What we want to do is find out how Q compares with KSP. If Q is equal to KSP, then that means this is an equilibrium, and that means that there would be some solid present. If Q is bigger than KSP, then that means there's going to be probably a lot of precipitate. But if Q is smaller than KSP, that would mean that the reaction would be shifted all the way to the right, and there would not be any solid form, no precipitate. So we want to find out the size of Q. Q, of course, is going to be Ce3 plus concentration times IO3 1 minus concentration cubed. So we have to find out what is this concentration and what is this concentration in our mixture. CeNO33 is completely soluble, and so the concentration of Ce3 plus is going to be the same as the concentration of CeNO33. And so that means the amount of cerium nitrate in our mixture would be given by 750 milliliters times the concentration, 4 times 10 to the negative third moles per liter, divided by the total volume. We're mixing 750 and 300, so that gives us 1,050 milliliters total. And so this gives us our concentration of Ce3 plus in moles per liter. When we do the math, we come out with 0.00286 moles per liter. We can do the same thing for potassium iodate because potassium salts, group 1 salts, are all completely soluble. So we can take our 300 milliliters, multiply by the concentration of potassium iodate, which is 2 times 10 to the negative 2, and then divide by the total volume of 1,050 milliliters. And that tells us the molar concentration of iodate ion, which ends up being small, 5.71 times 10 to the negative 13th. So what's Q? Well, Q is equal to 0.00286, that's the concentration of Ce3 plus, times 5.71 times 10 to the negative 4th cubed. So that comes out to 5.34 times 10 to the negative 13th. KSP is 10 to the negative 10th, so Q is less than KSP. In that case, we have no precipitate because this reaction is going to be shifting to the right, which means no solid will have formed. Let's do 2 more predicting precipitation problems, and we'll do these in a separate workspace where there's more room to work. In this problem, we're mixing together 100 milliliters of a solution of lead nitrate and 200 milliliters of a different solution with sodium iodide together. And the question is, what are the lead 2 plus and iodide 1 minus concentrations after they're mixed? And the PbI2 KSP is given here as well. So when these are mixed together, this equilibrium could get established. PbI2 solid could be at equilibrium with Pb2 plus and 2I minus in aqueous solution. Now, if any solid has formed, then that means the concentration of Pb2 plus and I minus are going to be given by this equilibrium. But if Q is smaller than KSP, that means we will not be at this equilibrium yet, and no precipitate would have formed. So let's first of all figure out what Q is. So the expression for Q is going to be concentration of Pb2 plus times concentration of I1 minus squared. So we have to find out the concentrations of both of these species to be able to calculate Q. So what's the concentration of lead? Well, every lead nitrate that dissolves is going to give us one lead-2 ion. So we have 100 milliliters of solution, and it's 0.0500 moles of Pb2 plus is going to be released for every liter. So let's just put that as molarity. And then when we mix these solutions together, we're going to have 100 plus 200, which is 300 milliliters. So this gives us the concentration of Pb2 plus in this mixture in moles per liter. And when we calculate that out, we get 0.0167 molar. We can do the same kind of a calculation for the I minus concentration. We had 200 milliliters of that solution. Its concentration was 0.100 molar, I minus, and it was in that 300 milliliter mixture. When we calculate this out, we get 0.0667 moles per liter. So Q is equal to 0.0167 times 0.0667 squared, and that comes out to 7.43 times 10 to the negative 5. KSP is 10 to the minus 8, so Q is bigger than KSP. So that means that this reaction is at equilibrium with the solid. Okay, so now to determine what those concentrations are, let's turn to our Rice chart. Initial concentration, nothing for solid, zeros for the two aqueous ions. The change line will be a minus x plus 2x, and at equilibrium, Pb2 plus concentration will be x, I minus concentration will be 2x. So KSP, which is 1.4 times 10 to the negative 8th, is going to be equal to Pb2 plus concentration, which is x, times I minus concentration, which is 2x squared, which is 4x cubed. So we solve for x, and we found out that x is 0.0015 molar, and that is equal to the concentration of Pb2 plus. The concentration of I minus, well, that's just going to be double that. So that'll be 0.0030 moles per liter. Here's another one. A solution has 1 times 10 to the minus 4th molar copper 1 ion concentration and 2 times 10 to the minus 3rd molar lead 2 concentration. A source of iodide is gradually added to this solution, and the question here is, will lead iodide or copper 1 iodide precipitate out first? Well, the precipitate will form when the solution first becomes saturated, and that will happen when Q is equal to KSP. So for PbI2, that will occur when Q, which is concentration of lead 2 times concentration of I minus squared, is equal to KSP. KSP is given here, and it is 1.4 times 10 to the minus 8th. And we already know that the lead ion solution here is 2 times 10 to the negative 3rd. So at what iodide concentration squared would we end up with KSP? So we'll solve this for iodine concentration, and when you do the math, it comes out to 0.0026 molar. So once the iodide concentration reaches 0.0026 molar, this Q that we've calculated here would be equal to KSP, and you would get a precipitate. Now let's do it for the other substance. For CuI, Q would have to be, which is Cu plus times I minus, would have to be equal to KSP as well. And that is 5.3 times 10 to the minus 12th, which would have to be equal to our copper concentration, which we know to be 1 times 10 to the minus 4th molar, times the iodide concentration, and this is not squared this time. So solve for I minus concentration by dividing both sides by 1 times 10 to the minus 4, and you find out that the iodine concentration at precipitation here would be 5.3 times 10 to the minus 8th molar. Well, 5.3 times 10 to the minus 8th molar is much, much smaller than 0.0026 molar. So that means CuI would be the first one to precipitate out as that iodine ion is added.